Now, what we're going to be talking about now is Newton's method, which is a small portion of your final exam for MAT 135. And what Newton's method is trying to do is to find x-intercepts of functions. And the way you go about doing this is by using a rudimentary graph or by guessing numbers. So let's take a look at this function right here. So suppose I take a arbitrary point right here, let's say x1, and I find the tangent line to it right here, and that gives me a new point over here. Well, this right here, let's call it x2, that's not the tangent, that's not the x-intercept, which is right here in red, but it's close to it. So now what you do is find the equation of this tangent line, and then you use this new point, x2, to find another point, once again, like right down here, and then we can find the other equation of the tangent line, and we get the third point, a new point now, which is x3. Now, that also is not the x-intercept, but it is fairly close. So what Newton's method encourages is, hopefully by repeating this process over and over, you get closer to the actual x-intercept. Now take a look at what I wrote over here. This is just a method on how to actually get the different points. So first you start off with your x1, and then you have your second point, x2, and the way to determine that is you take the first points subtracted by the function of f of x1 divided by the derivative of f of x1, and you do that the same for x3. You just lower the point by 1 and whatnot, and so on and so forth. Now the general equation for this is right here, where you're trying to find x to the n plus 1, whichever function that is, and it's always going to equal xn subtracted by the function of xn divided by the derivative of the function of xn. So let's take a look at this example found in exam paper 2011, question number 11. So we want to find where the function x to the 7 minus 1000, which I have graphed just down here, and we want to find out where it intersects the x-axis, and we want to find the solution correct to 8 decimal places. Okay, so I put in 2 into x over here, so we know that if you take 2 to the 7 minus 1000, you get a negative number, and if you take 3 to the 7 minus 1000, you get a positive number. We know that this function is a polynomial, so it's going to be continuous, and we know that there's going to be a solution between 2 and 3 using the intermediate value theorem. Alright, so now we're just going to use Newton's method to get closer to this intercept over here. So in this equation right here, the first part, it says we take the point, x to the n, and then we take the original function, x to the 7 minus 1000, right here, and in the denominator, it says that we're just going to take the derivative of it. So the derivative of x to the 7 is just x to the 6. And then I'm just going to be plugging in x for the points that I have. Alright, so now we can pick a value for x1. Now suppose we pick 3. It doesn't matter. You can choose either 3 or 2. It's not a big deal. If you go back to the previous slide, now we know that to get x2, basically we have to subtract, put 3 into all the values of x1 that we have and figure out what the answer is. So we have 3 subtract 3 to the 7 minus 1000 divided by 7, 3 to the 6. Okay, so now to calculate this, you're going to have to pull out a calculator and just plug and chug. It's a little bit tedious, but we're going to have to do it. Now, we wanted to approximately 8 decimal places, so we're going to get the answer of 2.767391773. Okay, so now we're going to do the same for x of 3. Alright, so now for x of 3, we'll put in the x2 value that we just got, which is 2.76739173, subtracted by the same large number to the power of 7 minus 1,000, okay? And we divide this by 7 times that number again to the power of 6. And once again, like it is a bit tedious to calculate this, but that's what the question is asking. So we approximately get this final answer, 2.69008741. And that is our final answer for this question. Alright, so now we have our x to the 3 value. Now, we're going to have to be putting this value back into the original equation that we have right up here, up until x to the 6. So it is a very tedious equation to be putting it back into because it is such a long number, but it's just a quick plug and go, right? So I'm just going to write down the values that I got for x to the 4 and x to the 5 approximately, and then our final answer, which will be x to the 6. So once again, how I got x to the 4 is from the value of x3, I would put it back into this equation and compute it and get the answer. So for x4 we have that, and then for x5 2.68269580, and then our final answer is this. So this is the number that is going to be approximately between 2 and 3, and it's going to be our x-intercept.